Now, we know about this. So this is discovered in the lab, that we have the Aharanov-Bohm effect. Changing the magnetic field in the solenoid has a visible effect on the interference fringes. And from the paper, it's a beautiful paper, right? A really beautiful paper. They say exactly that in classical formalism, you use the potentials, but they don't appear. Notice, the fundamental equations of motion, they say, the fundamental equations of motion can always be expressed directly in terms of the fields alone. A and phi don't show up in the nomology, or don't have to anyway. They don't in the way that's normally presented. But in quantum mechanics, you seem to need to mention A and phi, which should strike you already as a little odd, right? If what's really real is E and B, why do I have to talk about A and phi? And then they say, now we're going to show that actually there are empirical indications that A and phi are physically real. So now we say, let's just take that hint and now put over here, instead of E and B, put A and phi. There, now in my fundamental physical ontology, I have to rewrite everything here in terms of A and phi. And here I do nothing else, which what does it mean? I no longer have determinism at all. I have a radical kind of indeterminism, because everything that I thought of before as just a gauge transformation is now a transformation that changes what the physical things are doing. And specifying what A and phi do up to any time leaves open an infinite number of ways for A and phi to continue after that time, which is what we normally think of as constitutes changing gauge at that time. So the result of taking A and phi seriously and not doing anything else leads to radical indeterminism. That doesn't sound too good. So I want to get rid of that. So what do? Well, here's something I can do. I can gauge fix. I can gauge fix many different ways. One way is with Lorentz gauge. And again, I only just found out that Lorentz is not Lorentz. And the Lorentz gauge, although it fits with the Lorentz transformation, they're two different guys. I didn't know. There's a lot of mistakes about that. And here's the definition of, so I say I still have these sort of mathematical degrees of freedom. I can cut them down by putting on extra constraints. So I put on this gauge constraint. That turns out not to nail everything down. To really completely gauge fix, I have to put a constraint on phi as you go out away infinitely far, at least in an island universe. And then I get back now determinism again, okay? And if I also, my nomology, which before had laws that were mixed between A and phi, they've now become separated. And both A and phi satisfy laws that look very similar, both using the D'Alembertian. And you say, that's really pretty. That's the mathematics yelling something at me. I don't know what it is yet, but it's telling me something. Let me think about that really hard. Version 7, I do the same thing, but I just have added over here. I can now take one of my laws out and move it over here to say, really what I have here is, again, the definition of minus rho is just the D'Alembertian of phi, which I have over here. And so I got rid of rho here. Okay, so that's my 7th version. But there are other ways to gauge fix, right? So here's the 8th version where I've gauge fixed using Coulomb gauge. And that's nice, first of all, because it's a complete gauge fix, right? It's a complete gauge. You have no further, once you've imposed div A equals 0, you're done. And furthermore, for calculation purposes, it's nice because now phi, the electric potential, is just the Coulomb potential calculated instantaneously for the distribution of charges throughout the universe. Yes? And so you get different equations over here. A is still a D'Alembertian equation. The Lorentz law is getting more and more kind of messed up down here, but we're not going to talk about that right now. And I can have, this is the last version, I can do the same thing and again derive the charge density, so I've moved the charge density from the nomology over here to the principles of derivative ontology. Now, this also, this is also screaming out at me, and this is the main point I want to make. So I said if you go into Lorentz gauge And you see, my fundamental laws, I've cleared out the other things, and the only fundamental laws I have are all D'Alembertian laws. And now, we all know enough relativity to say it's grabbing you by the lapels and saying, I am a relativistic theory, right? Because you can go into Minkowski spacetime and define the D'Alembertian like child's play, because it already has the right form, right? dx squared plus dy squared plus dz squared minus dt squared. So you can just convert this immediately into a form that lives in a relativistic spacetime, and you know immediately that the original theory was relativistically invariant, and so on. And that's what everybody's done, because they thought, yeah, relativity, that's good. The thing I want to point out is, what if you went a different way? What if you said, I like Coulomb gauge better, right? It's a complete gauge. It gives me this nice, simple way of calculating phi. What's it telling you? It's telling you, your A and your phi, they have a slightly different dynamics. The A part, the vector potential part, that lives naturally in a relativistic spacetime. But the phi part, because you're calculating phi by the instantaneous distribution of charge, needs a foliation. The phi part needs a slicing, a global slicing, the kind that you got out of absolute simultaneity in Newton's theory. And so you'd say, if I want to adapt this, it would live very nicely in a space-time that did have a relativistic structure for A, and in addition, had something like a global foliation for phi. Now, Roddy mentioned, and it's a very interesting thing that he mentioned it, that if you want to do Bohmian mechanics in a relativistic setting, here's an easy way to do it. Add a foliation. Use the foliation for specifying the guidance equation. You don't need it for specifying the Schrodinger equation, okay? And our division between A and phi here is now looking like a division between the dynamics of the quantum state and the dynamics of the particles that are directed by the quantum state. Now, you might say, why should I do that? Now, there's no reason to do it until you get Bell's theorem, right? So they wouldn't have done it in 1959, even having noticed this. So part of this is, what happens when I take A and phi seriously mathematically as representatives of what's physically real? But in 1959, you would not be tempted to do this. But after 1964, you ought to be really tempted to do this and say, it was sort of built in all along. That picture, that's a possible picture of the world. And everybody who says, but relativity, we must need a relativity, why would you think that Einstein would have gotten everything right about space-time before Bell? Before everybody knew you needed something non-local. He wasn't trying to explain anything non-local. Why think that relativity theory got to the very bottom of space-time structure and cannot be touched when you think about when it was developed and for what purpose, and what needed to be explained by it? So this is the kind of thing I think, if you get really clear about what you're doing, so the other thing is you could say, I don't like Lorentz gauge because I can't even gauge fix if I'm not in an island universe, and I'm not in an island universe, so that's not ideal, okay? So as I said, Lorentz gauge is screaming out, I am relativistic, and Coulomb gauge is screaming out, I live in a relativistic spacetime with an additional foliation. So I have some quotes from the, how much time do I have? Have we gone over already? -4. Okay. The rest of this, so let me, instead of reading this is all from the original 1959 paper. It's a beautiful paper, right? It's one of those papers, you read it and you understand it, and it's, it says this is really important. Pay attention. We've been thinking about electromagnetism wrong all this time. You all learned it wrong, and you all learned to think about gauge transformations in A and phi wrong. So these are just all, there are things that are here about searching for new beables. There are things about what possible responses can you have and what would the costs be. And I had wanted to read that, but there's not enough time. So we should have applause for the authors. This is David Bohm's centennial, as we know, and I don't know if Yakir is here, but there they are. I said, applause for the authors. This is a beautiful paper. And I had to hunt around. I didn't get anywhere near a picture of Aharanov at the age when he wrote this, and I'm sure this is later for Bohm. It was about the nearest thing I could find for Bohm. They were younger, okay? So I said to my wife, I feel like I'm going to the opera here. There's all these old people and then a scattering of young people. This is work they were doing when they were young, and they were, willing to shake things up a bit. And I hope the young people here take a clue out of that. So that is it.